first I'm going to go over the battery model. I didn't open up the document, but I think that equation, which is correct, so the way that equation talks about how you would calculate state of charge isn't wrong, but where it has the SOC new equals SOC old, and SOC is state of charge, it's the percentage of charge left in the battery pack. I don't know if we actually explained that in the document. The way that it says to do it is as a summation looking at D energy internal, which is DE int. But a summation over time where you have a changing energy value, if you integrate power, you get your change in energy. And so what it'll actually be is your motor here is going to you want to output the power that your motor requires. And then when you go into the battery, you have your power in, you want to add the accessory load, which in the document it states it as 600 watts. What you can think of that is normally on your engine, you have an alternator to keep your 12-volt system charged. It's about 600 watts or there around to run all of the systems on the car. That might be a little high, it might be a little low, depends on the car and what you have on. So you add those, and that's what we call your P terminal. So that's all of the power that's at the terminal. And then Rint is the internal resistance of your battery. That we model as a constant. In a real battery pack, it would vary, and for the purposes of this modeling, since we're not trying to get super accurate and super detailed, a constant internal resistance is actually fairly accurate. The way that a real battery works is when you pull a lot of current, or as the state of charge reaches the bottom or the top of its window, the internal resistance changes, and it'll also vary a lot with temperature. But since we don't model temperature, we use a power demand and not a current demand. We don't deal with that. And then VOC is the open circuit voltage. If you've taken the ECE classes, hopefully you remember what they mean by that. So if you're not loading it at all, that would be the voltage across the terminals. So the first thing that I would say that you would want to do is get P-term, have your internal resistance and your VOC, and you want to solve for current because those are the three things that you need. You have your terminal power divided by Rint. You're going to have to rearrange the equation because I think the equation is actually solving for the power at the terminals. That's pretty simple. Multiply by 4 and then have that as 4Rp, and then take the square of your open circuit voltage, take the square of that, subtract 4Rp, and then take the square root of that, and then take VOC squared and subtract the other value from it. And in order to get the current, because that's going to be that's going to end up as a voltage, so you need to divide by twice the internal resistance to get the current coming out of the battery pack. So once you have the current, to calculate the losses at the battery, multiply I by, that's not losses, that's VBAT, to figure out the actual voltage at the battery, because it's not going to be equal to your, it's not going to be equal to the open circuit voltage. When you start to load it, it'll actually change what the battery voltage is, and it's you can just take the current, multiply it by the internal resistance, and then take VOC and subtract that from it, and that'll give you VBAT. So essentially, as you pull current, what is called as voltage sag, when you pull a lot of current out of your battery, the voltage across the terminals actually drops. And so this is kind of trying to show that. If you've ever had a car that's got a battery that really doesn't like to hold charge, if you try to crank the engine over and over again, which is a ton of current coming through it, the voltage of the pack is going to start to, or not pack, the voltage of the battery is going to start to sag down, and then eventually that's going to kill your battery, and then you got to get jumped. So this is the loss calculation. So the heat, we treat the losses, we assume that they're all coming from heat in this simplified model. In a real battery pack, in the one in our vehicle, we actually have 7 modules, and then each module has 30 cells, 15 connected in series and 2 branches of those in parallel. So there's all kinds of connections going on, and each cell actually has a different state of charge than what we assume is the actual battery state of charge. We don't do that kind of stuff because if you multiply it by the internal resistance, the way that we've come up with this internal resistance is to take all of those losses into account. So we treat it as just a simple heat loss, and for a resistance, the heat loss is I squared R. So that's pretty simple. But then this right here is where it's actually, where we're logging it, and then also where we are breaking it up into propel and brake. And I'm hunting around for my mouse. So before you integrate to get your losses, what you want to do is you want to split off into these 2 branches. So you're going to end up really with 3 integrations. Up here, where I don't have any sort of saturation on it, I'm just trying to get the total battery losses. So if I integrate the power, then I'm going to get all losses associated with the battery pack. However, these 2, what I actually do is for this one, I only take positive battery power. And then for this one, I only take negative battery power. And so what we're doing there is we're breaking it down before we integrate. Then we're really only looking at what's coming into the pack and what's going out of the pack. So when you have regen braking, you can clearly see losses associated with regen braking because it's going to be charging the pack back up. And then you can see what losses are associated with propelling the vehicle. That's not so the big thing with that is if you didn't have a vehicle that had regen braking, you get none of your braking energy back. So if you were to do this with just your glider model, not even no powertrain components yet, if you look at the total energy consumption total energy consumption versus just the propel energy consumption is actually a lot higher on any given drive cycle. And the reason for that is because you're not regenerating, you're assuming that you don't get any of the braking energy back. With a conventional vehicle, you don't, so it makes a lot of sense to just use propel because it'll be what you're actually spending. You don't get any of your braking energy back. For a vehicle with regenerative braking, that is now energy that you can get back. And so it's really useful to be able to look at, okay, I can recover this energy, but I want to be able to look at how efficient are we at actually regenning. So if you have your total energy that you get back into the pack, and then, that's losses, but you can look at the total energy back into the pack during braking versus the total braking energy that you could have captured based on just in your glider model. There's some amount of energy available for capture, but you have, as you go back towards your battery, you have driveline losses, so now you have less energy. You've got your motor losses, so you have less energy. Then you have your battery losses, so you have less energy. But if you have it broken out like that, you can then look at, okay, well, the total braking energy available in the glider model versus how much we actually get back at the battery pack. If you divide the total of those, so the final value of the integration at the end of the simulation, you'll get the cycle average efficiency of regen braking. Similarly, you can do it with just propel, and you can look at cycle average efficiency of propelling the vehicle. And then if you look at total energy in and out of the pack, so I don't have it here. I think I'd break it out somewhere else. Probably in here. Yeah, so here we have DE int. So that's, at the end of the simulation, that's going to be the total energy consumed in the pack. And since we're a BEV, it's always going to be, we've consumed energy. So with that, we can look at that versus the total powertrain, or not powertrain, sorry, the total drive cycle energy needed for our given mass and all of that. And that comes from our glider. And we can look at the cycle average efficiency for the whole powertrain. And what you'll see is they're pretty different. They won't be like 20% versus 90%, but like you'll see, it's been a while since I've run this, but you might see a cycle average propel efficiency in the high 80s, high 90s, but your overall efficiency may be 60s or 70s. It depends on the drive cycle. So for HWFET, there's only one braking event, and that's at the very end. There's not a lot of energy available for braking there, so really propel and total energy are going to look pretty similar. But for something like UDDS, where you stop like every 2 or 3 minutes or so, there's a lot of energy there available for capture, and so it's pretty important to break it out into propel, brake, and total. Sorry, that's a bit of a sidetrack, but that's why it's important to break out these losses and other things into propel, brake, and total. So do you guys have any questions? Okay, so SOC calculations, the next thing I'm going to go over. Like I said, the equation on there, there is a way you can implement that exact equation and it'll work. Because that's how I've had it in the past. But I think the best way to do it is this. So you have your open circuit voltage, you have your current. So when you multiply those together, you get the power coming out of the battery. That gain doesn't have to be there, and that's not negative P. So I'll put that to the workspace. Ignore that. This is why you don't do your demos live. You can also ignore this. So I take the battery power and I integrate it, and there I have DE int, so the change in internal energy at the battery pack. And this is why, for me, I keep discharging as positive and charging as negative. But as long as it works and you get the right answers at the end, it doesn't actually matter which way you have those in the battery pack. Everywhere else, I think it will matter. But so you have your internal energy. You divide that by your total energy capacity, and make sure that this. You can see I do all kinds of things. I multiply by 1,000, divide by 3,600, because the way that I've stored the energy capacities in kilowatt hours, and this is where you gotta make sure you keep track of units, this is in joules. So you gotta get to watt hours and then to joules to make sure that you have the correct units. And then I take that and I subtract that from my initial state of charge. And since this is going to change across the entirety of the cycle, this is going to represent the current state of charge at any point during the cycle. This I set in my workspace, and you can see later on when we get to series vehicles, this will be pretty important because series vehicle has an engine as well. So if you set your initial state of charge really low, the engine's going to kick on, you're going to burn fuel. If it's really high, obviously the engine's not gonna, the engine's not gonna come on. So that's how I suggest that you calculate state of charge. There, you can do essentially find DE int, and then use like a summation block, and just feed it back in with a delay block. But I think integrators are better. Delay blocks can cause some really strange things to happen if you're using fixed time steps versus variable time steps. Sorry, I'll get you guys out of here soon. So, yeah, I know, patented Sam Reinsel soon. So this, I think, you'll find way easier to deal with, is going to throw way less problems as long as it's implemented properly. So yeah, that's the battery. If you want, I can, yeah.